Hello, everybody, and welcome back. This is Dr. Gardner at the University of Montana, and today we're going to be talking about storage, subsurface storage, and release of water from groundwater. So when we pump a well, or when the water table drops, or the head in a well drops, we're removing water from the system. And anytime we remove water from a groundwater system, we release water from storage. So today we're going to talk about where does water come from storage? We can drop the head, we can pump water out of an aquifer and still remain fully saturated. So there's a variety of sources of storage. And then we're going to talk about the relationship between that drop in head and the amount of water that we've released, which is a fundamental property of an aquifer. So grab your pens and pencils and let's get to work talking about storage. Okay, so at its very fundamental level, storage is the that's bad writing, is the relationship between the change in head in hydraulic head and the volume of water in the porous media. And it's important to recognize that this relationship can go either way. We can be adding water into the system and the head rises and we've added water, or we can drain water and the head falls and we release water. So we're going to go through some definitions here. And we're going to talk about the first. We'll start off talking about two different kinds of aquifers: a confined aquifer, and then we'll talk about an unconfined aquifer. All right. So let's define our first storage parameter, and that's called the storativity. All right, and this will get the big S. All right, and we're going to start off thinking about confined aquifers. And so the thing about a confined aquifer is that it has a saturated aquitard as its upper boundary, and the pores never drain. So a confined aquifer we release water from storage even though we never drain the aquifer. And some days this note-taking program I use is really slow and drawing is harder than others. And that is happening today. Okay, so So we're releasing water even though we're not draining pore space. So we do not drain pores. They remain fully saturated. And the source, well, we'll talk about the source of storage in this case, but just in your mind, think we're not draining the pores here. So let's first define storativity. And it's defined as the volume of water released divided by the volume of the head drop. And we'll talk about what this is in just a sec. So this is, let's just do the units, length cubed over length cubed. So this is unitless. All right. And what do I mean? What is storativity? Well, let's say I've got a column here. Of porous media. All right, and here's my aquifer. Here's the top of the aquifer, and up here is a confining layer. And I've got a well that goes down into my aquifer here. And the water level in my aquifer starts off up here at H naught. All right. And I pump, or I magically am able to drain water out of this column. And I drain some volume of water, VW, out of the column. And when I do that, my head drops here to H1. All right, so if my head started off at H naught, it dropped to H1. And let's say that my column has some area here, A, sub C, the area of, this is the flat area of the column. All right, so what I mean by the volume of the head drop is that is the volume of the, I guess it's aquifer material that, well, it's the area of the aquifer material multiplied by the head drop. So here, my volume of head drop is equal to AC times H naught minus H1. All right, so it's basically the area of the aquifer multiplied by the total drop in head. All right. And the storativity is the relationship between the volume of water I release and how much volume of head drop I have. All right. So it's this dimensionless ratio that that relates this volume of water that's drained to the volume of head drop. Okay, let's say that my aquifer has some thickness. B. All right, so this is the thickness of my aquifer, which is this porous media here, and this is the aquitard. So B is my thickness. We can define another term here, which we call the specific storage. all right? And it gets this symbol S sub S. And S sub S is equal to the volume of water drained divided by the volume of the head drop, all right, and multiplied by 1 over the thickness. All right, and so what this really does is take the storativity and normalize it by the thickness of the aquifer. So we could also write this as the storativity normalized by the thickness of the aquifer. All right, so this is the definition of specific storage. And the units here, well, this one is unitless and we have 1 over length. So the units are 1 over length. So another important relationship here, it's just the inverse. S is equal to S times B. All right, so what are the sources of storage here? So all right, so let's imagine this mythical confined aquifer that receives no lateral flow from anywhere. It's what we call completely confined. It has an upper layer, a bottom layer, and 2 sides, and no water is allowed to move into this aquifer. I can pump water out of this aquifer and I will not initially drain the pores, all right? And the reason for that is that as I lower the pressure in the aquifer, my porous media compresses, right? So my porosity gets smaller, and my water, as I depressure it, expands a little bit. So there's 2 sources of storage in this mythical aquifer, or in any confined aquifer. One is the expansion of the water. So this is expansion or compression of the water as pressure either is released or increases. And then 2 is the expansion or compression of the porous media. And we will end up basically deriving this, but I can write this as the specific storage is equal to rho WG times alpha plus N beta sub W, where alpha is defined as 1 over V REV times dV REV. Sorry, let's do this. dN dP, and beta sub water is 1 over V sub water dV water dP. I don't think these should be squiggles. Here they should be straight D's. That's important. Getting sloppy. Okay. So this is the compressibility of water, or sorry, compressibility of the porous media. And this is the compressibility of water. All right, and so the specific storage is in a confined aquifer, is the only source of storage, and it can be defined this way. So we'll circle this guy because it's important. All right. So now let's think about storage in an unconfined aquifer. All right, so here, now in an unconfined aquifer, the water table is the top of the aquifer. All right, if I put a well into an unconfined aquifer, the water table rises to the level of the water table. And so if I pump, I am dropping the water table. All right, I'm dropping the head, I'm dropping the water table, and I'm draining pores. So when we pump out or when we change the storage in an unconfined aquifer, we drain. Or fill pores. All right, and so here, if I, so we drain or fill pores. So we've got 3 mechanisms of storage here. We also have expansion of water. Expansion of water. And contraction of pore space. And the same goes if we're adding storage, we fill pores and we compress water. Or expand pores. All right, so in a unconfined aquifer, we're gonna define something here, specific yield. And specific yield, SY, is defined as the volume of water released under gravity drainage, all right, over the volume of the porous media drained. All right, so the way to think about this is if I have a chunk of porous media that's saturated and then I just let it drain under gravity, the volume of water that was drained out, normalized by the volume of that porous media, is the specific yield. All right, so that is the specific yield is essentially the measure of the storage released from gravity drainage of pores. So the total storage for an unconfined aquifer is, oh, this is bad news. Hold on, I must pause recording for a sec, I'll be right. Okay, after technical difficulties, the total storativity here is equal to S sub y, the specific yield, plus the specific storage times B. All right, and this represents the change in storage from gravity drainage of pores all right, and this is compression or expansion of water and porous media. All right, so storativity and specific storage expressly relate the head drop or the volume of head drop to the volume of water that we get out of an aquifer. And this is the last piece that we need to really think about deriving the groundwater flow equation. And it's a really important relationship because it relates changes in head to changes in the volume of water in our aquifer. All right, thanks for tuning in, and we will talk to you guys later.